Alright, let's talk about entropy today. Entropy is a very scary word, so you might think of a lot of math, maybe you can think of physics, but today, the entropy we're talking about isn't from these. It's from the field of information theory. What is information theory? It's theory regarding information. But at the end of this video, hopefully you understand what entropy in the context of information theory means. So you understand this equation which I'm writing down now, which is summation of negative p of j log p of j. What is this weird blob of math statements? You will understand soon. So let's imagine the context. Let's say Alice and Bob, B, are playing a game, and Alice wants to tell B some random string of letters. So let's say Alice can only say things from the letters A, B, C, and D. So there are only 4 letters. And so A might want to say, let's say B, A, C, D to B. So the question is, how many bits of information does B need to know to decipher what message A is trying to say? You might think, since there's 4 letters, so you need 2 to the power of 2 bits. Since there's 4 letters, you need log 4 equals to 2 bits per letter, and since there's 4 letters, you need 2 to the power of 4 equals to I'm bad at math. 2, 4, 6, around 16-ish, I think. Yeah. So you'd say, you need 16 bits of information to encode these 4 letters, but you fail to consider the probability distribution of these letters. Let's think of a special case. Let's say Alice is just screaming, and they just say A. As B, you would know that the next letter is always going to be A, and so with 100% probability, it's going to be A. And thus, information needed is 0 bits because you don't need to communicate anything. It's going to be A. However, let's say there's a different distribution. Let's just say, for example, it's a uniform distribution, and every single probability of it being A, P equals B, etc., is equals to 0.25 or 25%. Then how many bits would you need on average? Let's go back to the formula here on this funny equation here. I think it's best to explain if we apply it to the context of the question. So let's apply this equation here. We introduced the first part of the equation, which is called what's that called? Surprisal. Surprise, surprise. This means how surprised you are by the outcome. So the surprisal term is defined as 1 over P of J, where J is any choice you can make. So why is this surprisal? Let's say Pj is very high, which means that it's very common. Thus, when you have 1 over P over J, that means you predict the instance J, your output is very low, and thus you're not surprised because, it's expected, it's very high probability. However, when your probability of J is very low and it's rare, your 1 over Pj, or your surprisal, is going to be very, very high because you're very surprised that the output is actually the super rare output that you didn't expect. And thus, this is an important term in the equation. So, if you want to represent surprisal in an equation, and it has this annoying reciprocal function, we can use the magic of a log functions, and as you know, log functions, you can take away the power via the power rule. And so, if we add a log to this, and we represent 1 over Pj as P negative 1, you can just reformat the equation to be negative log Pj. From here, this looks very similar to what we had just now. All you need to add is just the pj in front, and this is the equation for entropy. So how does this relate to the question? This entropy equation gives you the average bits needed for communication. How does that work? Let's go back to A, B, C, D. So PA equals to PB equals to 0.25. So for any character, let's say PA, let's just use a case of PA. Your surprisal, your PA is 0.25, and as such your surprisal, P over 0.2 A is equal to 1 over 0.25 is equal to 1 over 4 1 over 4. I know, it's 1 over 1 over 4, so it's actually 4, yeah. So this shows that you need 4 bits. Actually, no, there are 4 possible instances. I'm stupid. Wait, never mind, that's not what it means. When you put that back into the equation, so negative log PA, you get negative, if you sub everything back in, it's log 2 of 4, which is 2, which correctly shows you need 2 bits to represent this information of A. And thus, if you work it out, if you add PA in front of this equation, you have P of A, which is 0.25. 0.25 times 2 equals to 0.5. This by itself doesn't mean anything, but in summary, adding the P of A means that the probability, you distribute this output according to its probability. So let's say a super rare variable, let's say a super rare outcome, let's say 0.001, maybe it might need like 100 bits, I don't know, I'm just saying random numbers. But since it's very rare, the average number of bits you need is less, and so it will be offset by the value. So 0.001 times 0.100 equals maybe 0.1. So yeah, the point of the first probability is to account for how common it is, and the second half is how surprising it is when it comes out. And so this will give you the average number of bits you need, because let's say if we continue calculating the number, and since we know that all 4 of them have a probability of 0.5, so for PB, PC, and PD, all the outputs of this will also be 0.5, and hence the summation of such will be 2, which is the correct answer because 2 bits for each of them, and they all have equal probability. However, when they do not have an equal probability, this is where the use of this entropy function comes in. Hopefully this is an eye-opener into entropy. This may not be very clear, but if you're interested, please look it up. It's information theory entropy, and hopefully you learn something from this video.